Well, hello everybody. This is the beginning of the graduate level course, Geostatistical Subsurface Modeling. I think in the calendar for UT it's listed as Stochastic Subsurface Modeling or Stochastic Modeling of the Subsurface or something like that. Whatever it's called, this is what it's going to be, and let's just get started with it. This is the first lecture, so what we'll do here is we'll have a really quick summary of who I am. There will be a lot of new students in the course, about half the students from the Jackson School of Geosciences. So let me get into that. So who am I? Well, first and foremost, my last name is pronounced Perch. I've been informed by Ukrainians that I'm not saying it right. However, it is over 100 years in Canada. We lost the ability to pronounce our last name, and that's what we've accepted it to be. I'm new to UT. I just left industry a year ago. It means everything is new. It means course material is new. This is the second time I've conducted this course. I'm making lots of changes to the class. You'll see that. What does that mean? I didn't write it down, but what I was thinking was I make mistakes. I'm completely open to advice. If there's an opportunity to improve and so forth, I'm always interested in that information. I want to help. I've done this. I have about 17 years of experience in consulting, teaching, leading, conducting industrial R&D and statistical modeling, reservoir modeling, uncertainty characterization, and so forth. And so everything I'm teaching, I know how this is actually done in industry. When I was at Chevron, I had the opportunity to review reservoir modeling work all over the company, all over the world. I had the opportunity to teach it, and I had the opportunity to conduct research in it. I left industry about a year ago to teach. Really enjoy teaching. So I'm motivated to try to do the best I can with this class. The other thing too is I'll say all the time in class that I believe in democratic principles, which means that if you have ideas in class, you have feedback on improving the learning opportunities, or even to manage the course load, let me know. I'm always happy to discuss. I'm always happy to improve. I'm very flexible. For instance, last term, about a couple lectures in, my students said, boy, Dr. Perch, it'd be really useful if you were to record all your lectures. And so I started recording all my lectures like I am right now, recorded them outside of class so that there is good sound quality. It also provides me the opportunity to really focus on the presentation for the video rather than, say, half the conversation is cut out while I'm interacting with students if I was to record during the classroom time. So this optimizes this idea of providing the best product, I think, to support the students. But it was feedback saying, why don't you record all your lectures? I did it. I put them out on YouTube, and I think that was a very good thing to do. If there's other ideas, I'm always happy to entertain those. I'm available. I have an open door policy. You're one of my students. You can drop by my office. If the door is closed, it probably means I'm just playing music, recording a video. No worries. Just knock. Come on in. It's okay. I'm always happy to discuss. I am an engineer, but my BSc is in mining engineering, which is basically where I was from, a form of geologic engineering. I had a lot of courses I took courses in stratigraphy, in mineralogy, in rock mechanics, slope stability, structures. I've been through a lot of even contaminant transport, hydrology courses. So I have quite a bit of geo in my background. In addition to that, my PhD was in quantitative geology. I had committee members such as Octavian Kanunu up in University of Alberta, who's well known in sequence stratigraphy, and I spent 13 years in Chevron in earth sciences R&D, working with geologists, geophysicists on reservoir modeling. So the summary of all of that is I speak geo. I'm also a modeler who strongly believes that we should understand the phenomenon that we're modeling, and we are modeling the subsurface. We should understand the geology. The other thing I should say is that I am active in outreach, social media, professional organizations. I'm not saying this to brag, but I'm associate editor of Computers and Geosciences. I was just put on the editorial board of Mathematical Geosciences, both for the International Association of Mathematical Geosciences. So a lot of math, a lot of geosciences. I've just been nominated or put in a chair position for the SPE Data Analytics Technical Section. That's international, not one of the local groups, which is awesome. That's a lot of fun. And I authored a book. On Twitter, I'm the Geostats Guy. On GitHub, I'm the Geostats Guy. And on YouTube, all of my lectures are available under Geostats Guy Lectures. So what will you learn during the class? So don't worry, I'll never do that again for the remainder of the class. I will not spend a bunch of time talking about myself. I think it's good. You know who I am, where I'm coming from. I hope it helps you understand my perspective, my motivations, and so forth. Okay, so what are you going to learn from this class? You're going to learn about data analytics, spatial data analytics, subsurface data analytics, geostatistics, the theory, the methods, the practice, how we do subsurface modeling, how do we build the workflows in order to accomplish that. We're going to learn what is done currently, what's established practice, what should be done, what are the gaps in that established practice, and what are in fact the best practices. What could be done, novel, innovative approaches that would really push it forward. We won't spend too much time on that, but I think it's a good idea to provide some of that so that you come into kind of looking forward, thinking forward about new opportunities. How to influence what gets done. How to critically evaluate subsurface modeling work. If you were on a project team, an asset team, and you had to evaluate and look at the model that's being built, what are the questions you should be asking? What are the diagnostic types of features or components that you should be looking at? How to do it yourself. Maybe you want to at some point develop your own workflows. Well, you should know how to do that yourself, and we'll do that in the class. You'll get a chance to be building your own workflows, getting the job done yourself. How to communicate what is done. How do you report to people who may not be knowledgeable in the field of modeling in a way that they will understand and be able to evaluate that work and be able to support their decision making. Everything we do in subsurface modeling is all about decision support. Communication is critical to make sure we can do that. So how are we going to do that? That's what we want to teach you in this class, how we're going to accomplish that. Well, we're going to do some role playing. I like improv. It's kind of like improv, I guess, except for it won't be comedy, but I do make jokes sometimes. Anyway, we will operate the class as a term-long role-playing effort, where basically we'll have the class as a subsurface project team, an asset team, and that's going to be starring myself as the subsurface asset manager, and each one of you will be a subsurface modeler on my team. You're working for me on my team, and we're working within some type of a large company, an industry. And so all term long, we'll be working on the same project, but we will progress it through all the fundamental steps of subsurface modeling. So the students will have the opportunity to work with realistic synthetic data sets to gain practical experience. In fact, I just finished the Python code in order to make those randomly for each one of the students, but I'll comment on that. Complete a comprehensive reservoir, or I should say subsurface modeling project, including initial data analysis and cleaning. Often you'll hear that 80% of the effort is data preparation and cleaning. We'll provide data that's pretty clean, so we won't have to spend 80% of our term doing that. Univariate, multivariate, and spatial analysis, estimation and simulation of reservoir properties, and also model checking, post-processing. Lots of things we can do with the model when we build models, and then to support and make decisions in the presence of uncertainty. The students will be expected to prepare and present project updates as we go along, consistent with what I would have expected when I was a program manager or a project leader within industry. I'm going to expect that type of presentation. I'll help you get that, to be able to do that. So really, How are we going to be able to do that? This is a good question after what we've all talked about. It might seem ambitious as far as what I've laid out for the goals for this course. Well, the way we're going to accomplish this is that you can have resources available to you that are going to help you. There's in-class lectures. They will cover all the necessary theory, the methods, the practice, the strategies, and the workflow designs. That will be given to you in lectures. Now, during the lectures, the class lectures are going to be recorded and put on YouTube for review, and they'll be recorded just like this is right now from my office, so it's good sound quality and so forth. You can use the review. I tend to talk pretty quick, so I'm finding my students don't actually have to speed up my lectures 2 times or what in order to listen to me. I think it's more efficient, but you can always pause me if you have to. All lectures, demos, workflows from the undergraduate class are also available on YouTube, GitHub, and so forth. And these are pretty useful because a lot of the basic concepts, the theory, was taught in the undergrad course too. In fact, I will be leveraging it from it at times, not everything, but we will go into much more practice than we did in undergrad, but a lot of theory is there. So all of those lectures are available on GeoStat Lectures channel on YouTube. There's, I think, 40 or so lectures there and are available to you. And on GitHub, there are a lot of workflows available to you. You can download. In fact, many of the critical steps that we have for this term-long project, I've already put together sample workflows with generic data sets in order to accomplish a lot of these steps. So this will be there to support you, to help you put together your own custom workflows with your own data. Why learn about geostatistical subsurface modeling? You may have got to this point right now and you're having this realization of, why would I spend this time? Why would I spend all this effort doing this, working on these workflows, this role-playing exercise in this course in order to learn about subsurface modeling? And so, level 1, you want a basic understanding of subsurface modeling. Most reservoir asset subsurface teams are working with 3-dimensional models of the subsurface. For any major capital project, that's a given. There's going to be 3-dimensional modeling. If you're going to work with the subsurface, you're going to be exposed to stochastic reservoir models. And if that's happening within your subsurface asset team, what generally happens is they'll be at the center. There'll be the model construction with all this information integrated into it. It's essential for you to understand how these models are built, to be cognizant, to be aware of how they're being built. What's the next? Level 2 would be you want to improve communication. Once again, the reservoir modeler is going to sit in the middle of the subsurface team. I'm not suggesting that they're the most important member of the subsurface asset team, but they are in the middle. They are interfacing with all of the other disciplines in the subsurface team. And they're integrating all that available engineering, geologic, and geophysical information into the subsurface model. And so the best thing to do is to improve your capabilities in modeling so you can improve your communication and your integration of your concepts, your information into the subsurface asset team. You'll have better communication on the team. That's all. Let's just say you'll have better communication across the team if you understand what's going on with the modeling. Level 3 would be where we now maximize our impact. Now, reservoir models are used directly to support to calculate the forecasts and other types of results from the subsurface that are then used to support decision making. If you want to best integrate your knowledge into the subsurface model, you should understand about how reservoir modeling gets done so you can make sure your engineering, your geophysical, your geologic information gets into the subsurface. If your expertise does not impact the model, that's the worst case scenario, you may not impact the development decision, the exploration decision, or whatever decision it is, and then you don't have impact. We all want to have impact when we're out there working. Level 4. Well, level 4 is where you go over to the dark side. You decide to become a reservoir modeler or subsurface modeler. In my experience, the vast majority of those who were participating in building these subsurface models were, in fact, engineers and geoscientists who learned on the job. If you're interested in that path, this course will be a very valuable opportunity for you to jump forward, to spring forward in the knowledge required in order to do that, to gain the theoretical knowledge, to learn about the best practice, so that you can be a good modeler. Black box uninformed reservoir modeling or subsurface modeling is dangerous. It results often in bad forecasts, and that results in bad decision making. In this class, you'll learn enough about what's going on under the hood to critically evaluate and improve reservoir models, to be a better subsurface or reservoir modeler. So how are we going to assign grades within this course? There's no quizzes, there's no examinations. The idea here is I want to incentivize the performance that would help you succeed within industry. In industry, you will succeed when you're able to integrate concepts. You're able to provide professional updates that provide your leadership with the information that they need in order to make decisions, and you yourself support and help make those decisions. So I will base the grade completely on project updates, which you'll see later are oral and written, a completed class project, which is going to be a compilation of all of those updates into a final report, and also class participation, the questions you ask of other groups or other individuals as they're presenting, and how you participate in class like that. Okay, textbook. There's no assigned textbook within this class, although there are books that could help you in this class. Now, I could also make my lecture notes available from the undergraduate course. That could be helpful. I'll probably upload them and make them available to you. The lectures are available to you. My book with Clayton Deutsch, I think, would be useful. I've asked the library to stock a couple extras of this book, specifically the library over in petroleum engineering. I could reach out to Geosystems and ask for the same thing. But that book is also available, of course, for purchase. I think if I was to recommend a single book, that would be the one I'd recommend. If you want to learn about the methods behind geostatistics, kind of more in detail, the Geostatistical Software Library and User's Guide is very good, Deutsch and Journal. And of course, Larry Lake, one of our full professors here in my department, wrote a very good book, Statistics for Petroleum Engineers and Geoscientists. That may be also useful to you. Now, if you want to hear about my thoughts around other books that could be of use or of interest to you, well, here's a list right here. Of course, I put the Geostatistical Library and User's Guide up top. There's also an Applied Geostatistics with SGEMS, which is a open source set of software for geostatistics developed at Stanford University. Remy Boucher and Wu provide a user's guide for that. There's an Introduction to Applied Geostatistics, which is the book by Ed Mo, known as the book from Ed Mo, Isaacs and Srivastava. Very readable, very readable. And there's a variety of other books right here listed. If anyone's interested, I, of course, have these books in my office if you want to check them out before you pick them up. What are the subsurface modeling steps that we will cover in this course? Well, our chapters of this course will follow, and the updates will follow these main steps within a subsurface modeling workflow. Now, we'll start with some prerequisites up front. We'll spend a couple lectures and we'll get into some practical things around maybe Python or around fundamental probability theory that I think is essential to get you started. But after that, it'll be very much focused on the steps of subsurface modeling. Data preparation, univariate multivariate analysis, spatial analysis, estimation and trend modeling, stochastic simulation, uncertainty analysis, how do you check your models, and then how do you make decisions in the presence of uncertainty with your models. For each one of these chapters, there will be lectures and demos. There will be examples of how we do this for subsurface inference and modeling, and then there'll be an opportunity for you to complete an update towards the final project and provide an update with documentation and presentation of that work. Now, let me just make a couple more comments about the project. What's the motivation? What's the idea? Well, the purpose of the project, provide you with hands-on experience to teach you the theory and then be able to thoughtfully, empirically get to experiment around, apply this theory to realistic subsurface modeling problems. The deliverables from it, well, you'll provide regular updates, documentation, and in-class presentations. I want you to gain from that experience with professional presentations and documentation, the style, the skills. I also want you to gain opportunities to learn about critical review of a subsurface project. So when you're not presenting, you have the opportunity to ask questions, clarification, questions that can in fact be quite challenging, which will help everybody come to a better solution. That's all about being a better observer, better at critical review of models. And I know in my professional career, I encountered a lot of people who did a very good job of asking those very good questions, finding those critical gaps and helping the project improve at the end. And I faced that a lot, and it made me better at what I do. Provide ample opportunity to demonstrate your knowledge. Tips for success. Work to demonstrate your knowledge of the theory, of the concepts. Don't just paste figures into a PowerPoint. Think about what they mean. Think about how to interpret them. Be very efficient with that. Ensure that you follow the guidelines and address topics provided in advance. Don't provide an update that doesn't actually address the fundamental technical questions or challenges that were given to you at the assignment, at the time of the assignment and for that update. Presentations and documentation must follow logical flow. They can't just be floating in the air. They have to be defendable, build up. You have to explain assumptions, limitations, and other considerations. If you do that, you're going to do very well in this class. For the project, I have already generated multiple synthetic truth data sets, and they are based on a simple two-dimensional multivariate spatial problem. It's 1 kilometer by 1 kilometer. And there's a variety of different attributes. There's facies, sandstone and shale. There's porosity, there's permeability, there's a seismic property, which is acoustic impedance, that you also will be able to work with. And that's exhaustively sampled at all locations. The other ones of the other properties of interest are going to be sampled only at limited locations within that 1 kilometer by 1 kilometer. Now, there are multiple truth data sets and sample sets for every one of the students, or we may use groups in the class. We'll see how that goes. And every single thing has been randomized. So what you'll find is that each one of these truth data sets, and in fact the sample sets from each one of them, are randomized, so they'll all be very different from each other. Software. What software should you use? Now, we could not have hands-on practice and opportunity to build your own workflows without using the computer. We have to do something with the computer to get that down. The point is, I refer you back to one of my first slides where I said I am democratic, or a believer in democratic principles. And so you're free to use any software you would like to complete the term-long project, as long as you meet the goals, provide me with the summaries, and that are going to be discussed in more detail just pretty quickly here, then it's all good. So what are some of the options that you could use for doing this? Well, you could use open source statistical and geostatistical software. The most simple approach would be just to use GeoSlib. Now, GeoSlib is the standard geostatistical library, and so you could just run the individual algorithms. You could build a workflow with .bat files that would run each one of those methods in sequence. You could produce a series of outputs, which could be output files, data files, and models, or PostScript files for your summaries and your reporting. You could do all of that in GeoSlib. And in fact, in fall of 2017, most of the groups did, in fact, complete this course just doing it like that. And I can provide examples, workflows, and so forth to help people do that. You could use R and RStudio. Their stats and GStats packages are actually pretty good. It's quite robust, it works quite well. And I could also provide example workflows. I had put them together for my undergrad course, and so those could be available to you too. You could do Python PyGeoSlib. PyGeoSlib is a package. It is more of a formal wrapper of the GeoSlib in Python. It's got its own kind of design. I've used it. I've developed example workflows. The package is not current. It's maintained, but it's not quite current, which means many students may run into problems trying to install it. You may have to go back to a previous version of Python. Because I found it became a bit of a headache in order to get that all working, but you could also do that. I have developed workflows using PyGeoSlib that can help you get started there. I put this in red. This is my recommended path forward: Python GeoStatsPI GeoSlib. What we do here is I'll give some more information about it right away, but basically it's my own. I've coded up GeoStatsPI as kind of a very simple wrapper of the GeoSlib with re-implementation of a lot of the kind of simple numerics or visualization. And that way you can build the entire workflow in Python. It's quite clean, it's easy to use, and all you need is the examples. You could work with the functions that I have in GeoStatsPI plus the executables. Now, another option would be to work with more commercial type software, such as Patrol. If you have access to Patrol, in our department, there's an educational license. Students can get access to Patrol. It is commonly used in industry for building subsurface models. So it would maybe make sense to use something like Patrol. I'm not going to expect that for this class. I'll make other comments about software right away here. There's also, of course, other commercial software with appropriate licenses that you could use, and so I list those here. I am completely open to whatever software you're comfortable using. Now, a couple more comments around software and coding. This is not a software coding class. So people have asked me, why don't you just teach Patrol? And that we could do that. Patrol has some very nice tutorials. We could try to teach that within a class. I don't think that that has high utility. The reason being is that, of course, Patrol is a highly specialized software suite. It receives regular updates. It changes. And so what you'll find is that there's so many details to Patrol. If you don't use it continuously, you start to lose it pretty quickly. And so you probably, by the time you finish and leave UT, you may not be current anymore. I think we're better served if we teach you the concepts for deeper understanding of how do you build workflows and for subsurface modeling. And then you're able to, when you get into a company, whatever software they're using, you'll understand those concepts, which will be general, in fact. It's amazing. Even the basic building blocks of what we did with GeoSlib from like 20 years ago is exactly what people do in Patrol. It's just more fancy with the GUIs and databases and so forth. But it's all basically the same thing. If you understand those deeper understanding of those concepts, you'll be able to use whatever software is available, come up to speed with get up to speed with how it works and be able to put that together. Now, workflows could be developed using very simple GeoSlib type methods. I'll comment on that. So no coding would be required at all. No advanced software would be required at all. That would be possible. Python in our approaches, you use available packages with very basic coding. You don't have to do really deep Python coding in order to do this. It's more about using the packages and putting workflows together in Python. So if people are interested, I have a variety of different demonstrations available for basics of Python. If a bunch of people are going to use Python in this course, I could run a couple of the lectures just on basics of building workflows in Python. Regardless, I got lots of example workflows for people to start with, and I'm always happy to do more to support people. Python's powerful. A basic ability to use Python probably looks pretty good on your CV. So I encourage that. Now, I want to emphasize this point right here. This class could be completed with very basic scripting and use of GeoSlib programs. So one option would be you just use .bat files, which is basically an example which shown right here. I in fact used .bat files to build the truth models back in 2017, not Python at that point. And so you could have all kinds of looping and conditional statements. You could do a lot of things in BAT files, and you could be able to build your workflow up, and it would not require any coding at all. So the reason I'm saying all of this is this course is completely accessible to any geoscientist or engineer, even somebody who showed up here today and said, I absolutely refuse to code and I don't want to learn complicated software. Then you could do it this way and you could have complete success in this course. You would not be at a disadvantage as far as the result from this class. But if you're not already convinced, please provide me with the opportunity to show you 2 slides. And on those 2 slides, I would like to try to convince you that in fact, coding would be of great benefit to you. And so here's some arguments for why coding should be something that all geoscientists and engineers should learn. Transparency. No compiler accepts hand-waving. Coding forces you to lay your logic bare for anybody, any scientist or engineer to review and look at your logical flow of your workflow. It's coded. There it is. Reproducibility. You run it, get an answer, hand it over, they run it, they get the same answer. One of the main concepts behind the scientific method, coding's pretty handy for that. Quantification. Programs need numbers in order to run. You need to feed the program. You're going to discover new ways to look at the world with quantitative methods. You will learn new things. Open source. Leverage the world of brilliance. Check out the packages. It's amazing what's available to you. How many workflows and packages are being shared freely all over the place. Very easy to install, all kinds of repositories for it, and you're able to run and try something new. I remember one day I learned about the Hurst coefficient. I thought that'd be really interesting to try it out for time series analysis. And within minutes I was calculating the Hurst coefficient. I downloaded one package, I was going. It was very great. Break down barriers. Don't come up with your engineering geoscience solution and throw it over the fence. Sit at the table with the developers, the people who are taking your knowledge and turning it into a tool. Sit at the table with them and share more of your subject matter expertise. Get a better product because you understand something about what they have to do to code it. Deployment. Come up with something great, code it up, share it with others, and multiply the impact. Leverage. Performance metrics or altruism, it doesn't matter. Your good work is going to benefit many others. And in the end, you're probably going to get recognized for it too. Efficiency. Minimize the boring parts of your job. Doesn't matter how scientific we are, there's going to be boring parts of your job. If you can build a set of scripts, some type of code that automates the common tasks, things that are boring, you spend more time doing engineering and science. Always time to do it again. How many times did you only do something once? Probably takes 2 to 4 times as long to script, to code, to automate a workflow. It's usually worth it. It turns out you'll have to often go back and redo it over and over again. Be like us. I hope this doesn't sound too arrogant. It will change you. Users will always feel limited. Programmers, they truly harness the power of their applications and their hardware. They feel empowered. And so that's why you might want to consider coding. Just in case you had not already been convinced, there's great benefit in coding. I have had coding in my entire life, in fact, it seems, all the way from when I was very young, coding on cassette tapes on my TI 99.4A, then my Amiga 1000, that I bought with my newspaper route, my Amiga, shucks, I went to Amiga 2000 after that, upgraded, and then of course to various different PCs and so forth. But coding always provided me with great benefit no matter what I was doing, what I was working on. It was great. Now, I want to just give a couple of caveats because people will hear me talk about coding and they may make some assumptions. Now, first of all, I'm not arrogant about it. Any type of scripting, any simple type of coding, workflow automation, matched appropriate to your working environment is great. It's all great. We don't all need to be C++ experts. I spent probably 13 years working with C++. I'm sure I'm not an expert in it. And I'm sure there's some C++ experts who've looked at my code and would agree with me. But anything is good. It's very flexible. I respect the experience component of geoscience engineering expertise. This is really beyond coding. This is the idea that it's essential to good workflow logic development. To best use the data, we need to really be focused on the geoscience and engineering. Coding's a tool to assist us in doing a better job as a geoscientist and engineer. Now, some expert judgment will remain subjective. When I say quantification and so forth, I'm not suggesting that we're replacing expertise with a machine. I'm not advocating for that in talking about the value of coding. All right, my caveats. I think I protected myself there. It's sincerely how I feel about that. So my recommendation for workflow construction. Once again, I said I had democratic values that I felt that people should be able to build the workflows however they like. I would recommend the use of open source methods with workflows in Python. I think Python, there's a lot of great resources right now. I would recommend leveraging the strength of the geostatistical library. Very robust, very well documented, example parameters, everything's available. So, and I would recommend if you're working in Python to work in Jupyter notebooks. So GeoStatsPI is a set of Python functions for most of the required workflow steps to support you in doing that. It includes visualization. The light numerics have also been re-implemented. The more heavy numerics, the kind of heavier programs like simulation, spatial estimation, and so forth, I have used wrappers in order to run the GeoSlib executables. And so the wrapping method is very simple. It writes out a parameter file, the data that's required by the GeoSlib program, runs the GeoSlib executable, and then reads in the results. Very simple. So this is the method I suggest, that you work with the Python GeoStatsPI that is wrapping and re-implementing basic GeoSlib. If any of these steps, if anything that you're doing seems onerous at any time, then let me know. I'll assist. None of this should be terrible. Now let me make a couple of comments about some of those components of my recommendation. Jupyter Notebooks. It really is, it's super cool. It's a web-based application where you have a set of blocks. Block, 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 and so forth. Each one of the blocks can include code, documentation, or results. And so this is documentation, this is code, documentation, code, result, and so forth. You can also work with a variety of kernels. In fact, when I say Jupyter, it does not mean that you have to work with Python. You could actually download and work with an R kernel, a C kernel, JavaScript kernel, or any other kernel, and you could use Jupyter Notebooks with those methods. In fact, I have a bunch of workflows examples in Jupyter Notebooks with R kernel because a lot of my students preferred the Jupyter Notebook to RStudio, and they like that. Now, once you're in the business of doing Jupyter Notebooks, there's so many cool things you can do. You can produce very professional looking workflows. The documentation is in Markdown, so you can actually put equations, links, you can make it look very cool. You can in fact use containers and run it online. Docker, you could put this entire workflow online and other people could run it in a container so they don't have to set up the environment. They can just run it online, experiment, and immediately see results. So it's all very powerful. Now, if you're going to work with Python, you don't need to know a lot. You don't have to be really in depth in the Python, but you want to be able to work with the basic elements, the basic objects that are created as part of a subsurface modeling workflow. And what are those basic objects? Well, they would include gridded data, like seismic data, and they would include tabulated data, like the well data. And so you'd want to learn about NumPy, which is a package that's very good for doing all kinds of numerics, but also for working with arrays of data, like a gridded data set. Pandas package provides excellent methodologies, the data frames for working with tables of data like we'd have from the well data. Now, I have tutorials available for the basics or the things that you need to know for arrays, gridded data, for data frames, well data. In order to build subsurface modeling workflows, I've made these tutorials, I put them on GitHub, and so they are Jupyter notebooks with many of the steps that you would need in order to build a subsurface modeling workflow. Now, if there's an interest from the students in the class, we could of course cover this in class. We could spend a couple lectures if most students are working in Python in order to do this. I could even do a lecture outside of class if people are interested in that. So what is GeoStatsPI? Well, it's something I've been coding. It's a set of functions in Python. These functions are the ones you need for most of the steps in building a subsurface model. Now, if they were visualization or light numerics, I recoded them in Python. And so there will be functions available to you like location map. All I did was use matplotlib and the standard geostatistical library types of parameters. And so people can quickly build location maps. If it's something like producing a varogram function plot, I have re-implemented vargplot directly in Python so people can do that, and that's just using matplotlib again. And so those are two examples right there. Heavy numerics such as spatial estimation simulation, I wrapped, as I mentioned before, the GeoSlib. Wrapping is very simple, as I mentioned before. It writes out the parameter file, it writes out the data. I have a bunch of functions included in GeoStatsPI that are able to convert between the GeoEAS, EAS format and in fact the format of, say, data frames or ND arrays, so you can move back and forth between GeoSlib and Python with your data sets. And so all of that is available to you. I've written this, I am constantly adding to it, I put it on GitHub, and so we can even augment it to help support the students with maybe some of the more tricky steps within the project. What's expected from you? You're going to work on a term-long project. Updates will be due every 2 weeks. The updates will include an oral presentation on the day that they're due. Only about 5 minutes, very brief, very concise, and then we'll have 2 minutes of questions, and we move to the next group. PowerPoint template is provided to you on Canvas. A written update is very, very concise. Here's a template right here. You'll see that it works out to be maybe 2 pages in total with figures. It's brief, it's concise, should not be onerous. Use efficient, creative figures to communicate. Don't just provide us with a document or me with a document that's going to be just pages and pages of figures. Think about how you can be very efficient with combining figures, communicating very efficiently. And I also have a Word document on Canvas for you. Here's the PowerPoint presentation update template, very simple. It's just the summary, executive summary, workflow, results, discussion, conclusions. It should be literally 5 slides in addition to the title slide. The final project, it's not that bad. It's going to be a compilation of all of the updates with the requested revisions. If there were revisions that I requested, and there will be, based on the discussion from the class and based on my input, there will be chances for you to improve on your work. Those will be expected. The documentation a bit enhanced, and then there'll be an additional challenge of a decision-making exercise that we will put into it, and you'll be expected to complete prior to handing in the final project. Academic dishonesty. Let me say, we are simulating a corporate environment. We all win together. Collaboration is completely encouraged. Consult with each other. I want you to do that. I want you all to learn together as a group. It's a real world type of situation. We have a network. We're connected to each other. You might be modeling in Tengiz, and you might talk to somebody else in the world who's modeling another carbonate reservoir, or you might be modeling at Jack and St. Malo, and then you're talking to somebody else who is modeling over in Block 14 in Angola. You would be talking to each other. Each of your data sets are completely different. The truth models are very different. So you won't be able to help each other with accuracy, but accuracy is not the challenge here, right? To build defendable workflows that use best practice is the challenge here. But each update final project must be unique work of each student. If the class is large, we may decide to form groups, in which case it will be the unique work of the group. Assignments. Hard copy of the update documents will be due at the start of the class. Presentations are given and graded in class. Contact me if you're going to be absent or if you have any other type of emergency. Late updates and presentations will be accepted with reasonable excuses. Illness, family emergencies, interviews, conferences. I support the fact that you have many important other things you're working on as far as being grad students, in some cases undergrads, and I get that. Disabilities, of course, if you have any accommodations, come see me. I am all about supporting and helping anybody. I want to ensure that everybody is comfortable and able to enjoy and benefit from this class. Classroom environment. Positive professional conduct. I think that's a great way to describe it. We're simulating a subsurface asset team meeting. Doesn't mean we're all like super gentle on each other. It doesn't mean we don't ask hard questions. In fact, the general tone should be searching and probing questions, but it should be very much like we're trying to encourage each other. We're trying to maximize each other's impact on the project. We're trying to be collaborative. We're trying to win together. Hard questions can help everyone learn. They can help us win together. If somebody's done something that you think they have an opportunity to improve, make the statement. It's totally cool. That's all good. We did that inside of industry. Actively participating and supporting a dialogue, and be enthusiastic. Avoid negative behaviors. Anything that's disruptive. Negative, disrespectful comments, of course, would not be okay. Anything that's unfocused. No use of electronics other than those needed to participate in the class. Cell phones will not be out. Laptops, if they're out, only if they're used to, say, follow along a lecture and so forth, not for any other type of use, checking the news, sports scores, or anything like that. Personal attacks, of course, would not be appropriate at any time. Presentations must not run over time, and that's part of professional conduct too. Imagine everybody in your audience will have a lot of responsibilities and competing pressures on their time. They will lose interest in what you're saying if they realize you're running late and they're uncertain about when they'll be able to escape. Some personality is fine, but be concise and be on message. All right. This class, we're going to teach theoretical and practical reservoir modeling. And we're going to do it with a lot of hands-on experience and opportunity to simulate what it's like within industry or within a company to be conducting an subsurface modeling exercise. And so now it begins. Of course, anybody who's watching or listening along here, at any time, you're welcome to send me questions. I am Michael Perch. I am an associate professor at University of Texas at Austin. I am also the GeoStats guy on Twitter, and I have all my lectures, GeoStats Guy lectures, on YouTube, and a lot of my workflows and methodologies and code are available on GitHub under GeoStats Guy too. All right, thank you.